Hello, welcome back to Aerospace and Mechanical Lab 2. Today we are going to discuss the second lab, heat transfer lab, which itself has three different parts. So first we're going to discuss a theory, and then we're going to talk about the lab, and in a separate video, we are going to teach you how to do the lab yourself. Okay. So again, review of heat transfer, the science of heat transfer. We're going to learn about transient and steady heat conduction. We will talk about free and forced convection and a lumped capacitance method. And eventually we will talk about the lab itself. So whenever you're talking about heat transfer, there are two terms that you need to define. First is temperature. Temperature is the amount of thermal energy available in a system. Temperature of a material does change based on the source of energy that is provided to the material. There are a lot of different sources available in the nature that will help you increase the thermal energy of a system or remove the thermal energy from the system. You have to keep in mind that higher the temperature of the material, it means that the higher Brownian motion, so essentially irregular movement of particles within a material. That's what it means. Heat flow or heat transfer is the movement of thermal energy from one location to another. The type of heat flow depends on the mechanism and the medium at which a heat is being transferred. And in general, our goal in heat transfer analysis is to find the equations and relationships between the changes in temperature and the amount of heat that is being transferred from one location to another location. There are a couple of different modes of heat transfer that we have to focus on. The first one is called conduction. Conduction is a transfer of heat through solids or a stationary fluid. And the one thing that is very important for conduction heat transfer is a direct physical contact. Essentially, what happens is you increase the energy of a molecule, and it starts in a solid, it will start vibrating more in place. And this higher vibration is going to cause a higher vibration in the adjacent molecule, and so on and so forth. So the conduction heat transfer is passed through molecular bonds, which essentially means, like in a gas, we don't really have any bonds between the molecules of a gas, meaning that there won't be any, or there will be very small amount of conduction heat transfer. Okay. So essentially, in most of our analysis, when we are dealing with conduction heat transfer, we are dealing with the two temperatures of the two sides of a block or at the two locations of a medium and the heat that is passing through that medium. You have to keep in mind that there's a difference between heat rate Q and heat flux Q double prime. Heat rate is equal to heat flux divided by the cross-sectional area, whatever that cross-sectional area is. Okay. Second mode of heat transfer that we have to talk about is convection. And these two modes are actually, we are going to analyze and use these two types of heat transfer in our experiment actually. Convection is essentially movement of higher energy molecules to a lower energy location. When you have higher energy molecule, let's look at this example right here. When you heat up the molecule here, the air molecules, whatever water molecules that are here, are going to heat up, are going to have a high energy, and this high energy is going to push them to move to this low energy location, which essentially means that these higher energy particles are going to replace lower energy particles here, which means that this region in the fluid is going to have a higher energy. That's how convection is done. And there are two different types of convection, advection and diffusion, but we don't really need to get into the nitty-gritty of things here. The two types of convection that we have to focus on is natural convection, which essentially means that you warm up a stationary fluid like this. You're going to have a higher energy fluid as a result of that warming up. That high energy fluid is going to move up and be replaced by a lower energy fluid. So just by act of heating up a gas or a liquid, any fluid in general, you are going to cause some sort of a movement in the gas. That's called free convection. But if you put a fan in front of a heater, which essentially if you force a fluid flow, if you have an external pressure differential causing the movement of the fluid, you are going to have forced convection. So the difference between free and forced convection is in one of them, movement is done by a fan. In the other one, movement of the gas or liquid is done because of the warming up of the liquid that is closer or gas that is closer to your hot surface. Okay, and the last type of heat transfer that we want to talk about is radiation. Radiation is the only form of heat transfer that is present in a vacuum, which essentially means that the transfer is done through photons, movement of photons or waves between two surfaces. That's how we receive energy from the sun. And any material which temperature is higher than 0 degrees Kelvin is going to emit energy. So all material emit energy. Radiative energy is not the strongest form of, in short distances, it's not the strongest form of heat transfer, radiation transfer. That's why we don't really include radiation heat transfer in our analysis of the day-to-day heat transfer cases. Yeah. Okay, so how should we analyze a conduction heat transfer problem? We need to employ the Fourier's law of conduction. What does the Fourier's law of conduction tell us? It says the heat rate that is passing through a medium like this is equals to the conductivity, heat conductivity of that medium, K, multiplied by the cross-sectional area for which it is here. Cross-sectional area is always normal to the direction of the movement of heat. So the cross-sectional area is not going to be this area, it's going to be this area, which is normal to the direction of heat transfer, multiplied by the temperature difference between the two surfaces or two measurement points, divided by the distance between the two measurements. So thickness, here we use D, but in the equation we use B, doesn't really matter, as long as you understand that this refers to the distance between the two measurements points. So essentially in a lab, you will be asked to find the conductivity of a material. We are going to simulate by adding a lot of insulations. We are going to simulate a one-dimensional heat transfer, and you will measure temperature at different points. You will measure the distance between the two measuring points. You will measure the area. You will know the heat rate, and using all of these, you can calculate the conductivity of your specimen, whatever that specimen is. Okay, but we have to understand that this formula is only applicable to steady state cases. What does a steady state case mean? It means that there won't be any fluctuations, temperature fluctuations, with the passing of time. We're going to see a graph later on to understand this point better. But let's say we cannot have a steady state condition. How should we deal with this? Well, essentially, we are not going to rely on any equations to calculate the conductivity of a transient case or not a steady state case. We are just going to use a device that is called the C-term. We're going to talk about that device later on. And that device is going to measure the conductivity of the material for us. We just have to do a statistical analysis and find the confidence interval. Okay, so first case, for us is to measure the conductivity of the material. One is using a steady state based device, and the other one is using a transient device. We're going to see all of these equipments later on in this lecture. Okay. Next step is to use convection heat transfer for, I guess, develop a convection heat transfer experiment to understand convection heat transfer better. So far in the previous scenario right here, we did not look at the heat transfer between this wall and the surrounding air or water or liquid, whatever that is, right? We did not look at any of this. But we need to bring that movement of air into play here, because that movement of air, the fluid moving on top of your surface, on top of a heated surface, is going to affect the temperature of the surface. If you have a very high speed fluid moving on top of it, the temperature is going to go down. There will be more cooling happening essentially, and vice versa. Okay, so how can we bring this into our analysis without making things too complicated? We are going to make two assumptions. First of all, the first assumption is conduction happens instantly. What does this mean? It essentially means that we are going to assume that within this, it is going to be a copper block for our experiments, but within this solid block, whatever that is, temperature is the same at all locations. So temperature here in the middle is going to be temperature at this wall and equal to the temperature at this wall. Conduction is happening instantly, and this is compared to convection between the fluid outside of these walls and this wall itself. So essentially, again, what this means is the conduction rate is much faster than the convection rate. That's why we don't really see any temperature distribution inside this block. It will reach thermal equilibrium, meaning that temperature is uniform all over, instantly, compared to the heat transfer with outside. Okay, I guess we did mention this point. So if you make this assumption, then you can use a method called lumped capacitance method. I don't want to get into the derivations of the formulas here, so just accept it as is. The idea is temperature here, temperature of the walls here, does change with time, but does not change with location. So think of this scenario. Think of a sphere. You heat up a sphere and you drop it in cold water, right? We are going to analyze the cooling of that sphere, right, over time. But the assumption we have made is that within the sphere, there is thermal equilibrium. So temperature is changing over time, but the temperature of the center of the sphere and the surface of the sphere is always the same. Okay, so for this specific scenario, the relationship, the temperature distribution can be found using this relationship. Okay, in this relationship, in this equation, T is a temperature at any time. Can be at time 0, the final time, in the middle, whatever. T infinity is the gaseous temperature or the liquid temperature that surrounds your sphere in the example that I just provided. And Ti is the initial temperature, which is a temperature at time 0. Again, T infinity, same thing. And on the right hand side, we have an exponential, which is E. I'm sure you know what an exponential is, but if you do not, please send me an email and we'll discuss this. And you have density of the material. This is density of your sphere in the example. You have the heat transfer coefficient, which is different from the conductivity of the solid block. Heat transfer coefficient is the ability of the gas that surrounds your sphere or any solid block to remove heat from that plug or to add heat from that plug. So higher heat transfer coefficient means that faster cooling or faster heating, depending on your scenario. And your goal in the second experiment is to actually measure a temperature change over time of a copper block and then to calculate the heat transfer coefficient. Area is the area of your copper block, your solid medium, whatever that is. Volume, T is the time that has passed. This is the heat capacity of your sphere in the example, and this is the volume of the sphere. So from the experiment, you are going to get this type of graph. You are going to get temperature. We have non-dimensionalized temperature and time here, which essentially means that we are replacing this whole ratio with a theta, right? This is the non-dimensional temperature. And then we are dividing time by this whole thing. But you don't really need to non-dimensionalize. It's just an example. You can just present a graph of changes of temperature with respect to time. So you are going to start with the temperature. This is the graph you're going to get from lab view. And then at the time 0, and then you are going to let it cool down as time passes. Essentially, there are going to be two scenarios. In one of the scenarios, we're going to put a fan in front of your specimen to simulate forced convection, and then another specimen is just going to be left dangling freely, and we're going to see the rate of the temperature drop, right? And using those two data, you are going to calculate the heat transfer coefficient. By the beginning, I said we made an assumption, right? We did make the assumption that the conduction is happening instantly. So the final step of this experiment is to make sure that assumption is correct. This is where we define a new parameter called the Biot number. The Biot number is essentially a measure of internal resistance, which is the conduction of the material, to the external resistance of the material, which is convection with the surrounding, right? So essentially, if this is smaller than 0.1, this tells us that the resistance to conduction is much smaller, at least 10 times smaller than the resistance to convection, meaning that conduction happens at a much faster rate, or we can assume safely that the conduction happens instantly, or conduction doesn't happen at all, like there is thermal equilibrium all over a solid block. Okay, so and using this definition, we can calculate the Biot number as using this formula. This is the heat transfer coefficient which you have calculated from the previous step, and this multiplied by L. L is the hydraulic diameter here, which is essentially your area divided by your volume divided by area. That's how you calculate the hydraulic diameter of anything. It doesn't have to be a sphere. It can be a cube or anything. You just have to calculate the area of the volume of your cube and divided by the area of the cube. And this is divided by the conductivity of your solid. In our case, this is a copper block. And if you do the calculation, if the value is smaller than 0.1, this tells you that your assumption about lump capacitance method was correct, and your calculations of heat transfer coefficient was also correct, and which is also means that your conclusion about forced convection and free convection is also correct. Okay. Moving on, we are going to talk about transient heat conduction more in the next slides. But this is your equipment. This is what you're going to see. This is our power supply. This power supply is going to generate power, and it's going to essentially heat up the top of this linear conduction device. At the bottom, we have a cooling. Then this is connected to water, and some cooling is happening, which means that we are going to have a temperature distribution between these 2 points, right? And we have thermocouples installed throughout this linear conduction device, that is going to help us make a couple of measurements of temperature measurements essentially. And you are going to see this type of temperature measurements, like temperature of each um, thermocouple as a function of time. So as you can see, we start with a transient scenario where the temperature of thermocouples is changing with respect to time. But at some point, it's usually after 20 to 30 minutes, the changes stop. This tells us that we have reached a steady state condition, and these temperatures are the ones we can record to put in this equation to calculate the conductivity. Okay, so if you run the experiment once, you are going to have 8 temperatures, 8 different temperatures, so 8 different delta T's with 8 different delta X's, which essentially means 7 different delta T's and 7 different delta X's, which essentially means that you can calculate 7 different conductivities. And you need to run a you need to do a descriptive statistics analysis and give us a confidence interval for the conductivity. Okay. Part 2 of the conductivity measurements is done using a C-therm device, which is essentially something like this that is connected to a bigger device and it's connected to a computer. You put your sample on top here, and what happens is that we are going to generate pulses, electrical pulses. And these electrical pulses are going to cause a temperature change in the surface here in this material, which in turn is going to cause a voltage drop in your circuitry. Okay. All of this is going to be used by the computer to convert that voltage drop to the conductivity of the material. So there is no calculation done here. Let's move on to this. There's no calculation done here. You just have to understand that the amount of temperature change or voltage drop in the system depends on the type of material. So if I have a lower conductivity sample, the penetration or temperature change is going to be smaller compared to a higher conductivity sample. And this happens every 2 or 3 seconds. Then it is going to send a lot of different pulses, and it will read a lot of different values for conductivity and effusivity, and a lot of, you're going to see in the lab that it is it will do a lot of calculations for you. You just need to take the conductivity and do a statistical analysis with it. Okay, so 2 parts of the lab. Part 3 of the lab is the lump capacitance method. So you are going to be given these type of devices. This is a thermocouple that is installed on a copper tube. You have to put this in a water heater to heat up to 80 degrees Celsius or in that ballpark, and then you just remove it. You have to heat up 2 thermocouples. And then you're going to put this you have to heat up 2 copper blocks. You're going to put the copper blocks in front of a fan and also in front of nothing and record the temperature change. Please make sure to watch the video recording and let me know if you have any questions. Have a good day.